Hi, I'm Gareth Spence and welcome to Tech Talk. At OFC, one of the most prestigious awards given to a company is the invitation to deliver a paper. Each year, only a limited number of the papers presented at the conference are invited papers. At this year's show, Adtran was awarded this honor. To provide details on the paper, I'm joined by Adtran's Sorin Tibuleac. Sorin, before we dive into the paper, can you explain what it means for Adtran to be selected for this honor?
It was indeed an honor, and we're delighted to receive this invitation. As you said, most papers presented here are not invited paper, only a subset are invited paper. And what the organizers are looking for generally are papers which have a significant new contribution in the field, results that are of great interest to other researchers, to the industry in general. And we had a post-deadline paper last year that was highly ranked, and our invitation to deliver a paper this year was based on the post-deadline last year.
What was so remarkable about last year's paper that allowed it to be accepted as a post-deadline paper and that prompted this year's invitation?
So last year we had the opportunity to test in the field what was then a brand new technology from Acacia, transceiver technology that incorporated their latest generation of DSP and optoelectronic chips, which had up to 140 gigabaud, so 140 symbols per second, and could tune the data rate from 400 gigabit all the way to 1.2 terabit per second. And we had the opportunity to test this in a field environment in one of our customer networks, NiserNet. So we wrote this paper jointly with NiserNet and with Acacia based on results in the field. Notably, we had an optical line system that had been deployed in NiserNet several years ago. And we were able to, even though we only had a couple of days for testing, we were able to set up this new transceiver and try to see what distances we can cover. And we obtained at record distances 800 gigabit per second up to 2,200 kilometers distance, and then at 1 terabit per second also 860 kilometers. Those are record distances at the time at these data rates. That was a brand new transceiver at the time. It was very, very interesting. In the meantime, Acacia has sold many of this large volume.
And what is the focus of this year's paper?
So this year, what we wanted to do now is take that same transceiver technology, bring it into the lab, where we can do a more detailed analysis of the performance. Since this transponder has a significant flexibility in terms of the data rate that it can offer, and also various options for symbol rates and settings at each data rate, we wanted to see how it would perform in various network conditions. So in the lab, we set up some links that replicate typical access network, typical core network, and submarine network. And we tested the maximum data rates we can obtain in some of these applications, and what are the optimum settings to obtain them. So specifically, we had an access link that had fixed wavelength with a gridless MAX-DMAX and a 100-kilometer standard single-mode fiber link. And we were able to reach 1.2 terabit per second on that link. A separate test was done on a core network where we had, again, standard single-mode fiber, 100-kilometer spans, and Raman EFA amplification, ROADMs, our own optical line system that we have deployed already, nothing futuristic there. We were able to do 800 gigabit with a fully loaded C-band spectrum all the way, so 800 gigabit all the way to 1,800 kilometers, and 1 terabit up to 1,200 kilometers. So these were very, very long distances. And then a third category of tests were on subsea links, so replicating submarine conditions, which means using the specific fiber that they use, specific amplifier distances that they use for submarine. And there we obtained at 800 gigabit per second over 7,000 kilometer distances, which are equivalent to traversing the Atlantic. And then we took it further, this time with 400 gigabit per second at even longer distances, going beyond 10,000 kilometers, which is equivalent to trans-Pacific. And just to see what the maximum distance could be, we tried all the way to 24,000 kilometers at 400 gigabit per second. So those are quite impressive distances achieved with this new technology.
What are some of the features enabled by the latest generation of high symbol, flexible, coherent transceivers?
So I would start with the symbol rate. So we have now up to 140 gigabaud as a symbol rate, and that's on a single carrier, single optical carrier. So what this achieves is for the same data rate, let's take 800 gigabit per second, compared to previous generations that could maybe achieve 800 gigabit per second, but with lower symbol rates. The higher symbol rates will provide the better performance, so we can achieve longer distances due to the higher symbol rate. So that's one key differentiator. This is possible by advancements in the optoelectronic technology that Acacia took advantage of, the DSP, 5 nanometer CMOS DSP, lots of improvements in the DSP algorithms. Another very important feature is the range of data rates that you can obtain with this. So as I mentioned previously, we did experiments from 400 gigabit per second all the way to 1.2 terabits per second. That's an impressive range of data rates. And what that does is it allows you to obtain the maximum capacity on any given link for any distance. Submarine will need to work with maybe 400 or 800 gigabit per second, but then shorter links, you can go all the way up to 1.2 terabits. And that is the same technology, the same transceiver. And yet another one that I would mention would be the flexibility in adjusting the symbol rate. That is really critical in order to maximize the distance and the capacity that you can transport in a given link, which may be subject to filtering, for example, going through ROADMs. So you only have a certain passband that you have to work with. So that symbol rate is really key to optimizing the performance. So I would mention these as the main features.
How do your tests differ from others that are being reported?
Generally, research papers tend to use the optimum conditions, the absolute best conditions you can create in a lab. What we did in our lab experiments, we tried to use typical conditions that our customers would have in the field. For example, we use standard single-mode fiber, not the latest generation of fiber, which would obviously give better performance. We use our legacy WDM equipment, our flexible ROADMs, our EFAs and Ramons, exactly what our customers have deployed in the field. So all of these create typical conditions, not necessarily under the best operating conditions you could design in the lab, but they're much more relevant for customers and for applications. And even under these conditions, we still have obtained impressive results, distances.
And why does all this matter to the industry?
So there are multiple concurring trends now. Obviously, the industry is looking for higher capacity. So this new latest generation does respond to that need of being able to provide higher capacity per fiber. But that may not be the main driver for some customers to deploy this. And the main driver always is cost per bit and cost per power consumption. So the cost per bit is really critical for the customers' bottom line and reducing their capital expenses. And the cost per per power consumption is also very important to reduce their operating expenses. So this technology advances in both of these metrics.
How will this paper impact Adtran's product roadmap going forward?
So the study that we did is very important in multiple ways. First, it allows us to understand what the limits are of the technology. So they are further, but we need to understand what it's capable of doing. And we achieve that through complex testing that we've done in our labs. A second benefit is that now that we know what it can achieve and what optimizations we need to do, this provides some requirements and some let's say, drivers, some requirements for our own line cards development. So it provides that type of information that's really critical. Thirdly, it allows us to be able to plan networks with this new technology, going to all the way to 800 or maybe 1.2 terabit per second. This is very important because customers who purchase a system from us, they are looking to upgrades in the future. So they want to understand what they'll be able to achieve with a new generation of transponders. And we now have that knowledge and we can provide those answers. And then also very important is to have these results and be able to show our customers that the optical line system that they've purchased can be upgraded to the latest technology with the highest symbol rates, wider bandwidth transceivers.
Sorin, thanks for joining me today.
You're welcome. Thank you.